In this video, we're going to talk about the content of section 9.1 from your textbook, which is how to develop confidence intervals around a population proportion, and sort of what does that even mean, right? Because I feel like for a lot of our students here, you don't necessarily know what we mean by a confidence interval or why it's useful, but that's the goal for this video. Several of the slides in the slide deck are going to be review from chapter 8. So I'm going to quickly review what we meant by the sample proportion and also what we mean by the population proportion. So we use lowercase p to talk about the population proportion, and given some type of Bernoulli trial, the population proportion is just the number of successes in the whole population divided by the population size. So just to give you an idea, maybe your population is dogs at the dog park. And we'll set up a little Bernoulli trial. So each dog represents a Bernoulli trial, and we'll call it a success if the dog is a border collie, and a failure if the dog is any other type of dog, right? So then my population proportion P would be just the ratio of the number of border collies at the dog park divided by the total number of dogs at the dog park. That's what we call the population proportion. Now, if we say X is the number of successes from the N Bernoulli trial, so X is just the number of border collies at the dog park, then we'll say the sample proportion is this, well, maybe I misspoke. We're going to say X is the number of successes from the N Bernoulli trials, where N is our sample size. And so that means if you're using our dog park metaphor, X isn't the total number of border collies at the dog park, but if we took a sample of just maybe 5 dogs or 10 dogs, right? Well, then our sample size N would be 10 for sampling 10 dogs, and X would be the number of border collies out of those 10 dogs that we randomly sampled from the population. So in that case, our sample proportion, we're going to use p hat to represent the sample proportion, and this is just going to be X divided by N. So it'd be the proportion of border collies in our sample of dogs. So notice the symbolic difference. We use just p for the population proportion, and we use p hat to represent the sample proportion. And you know that since X is just the sum of the number of Bernoulli trials, that means that X is a binomially distributed random variable. And that also means that since p hat is just some binomial random variable divided by a constant, that means p hat inherits some of this binomial shape. And I've said this before in chapter 8, but maybe I didn't show you, and so I actually have a visual today of what this looks like. So here in red, this is a binomial distribution, and my sample size here is 40, and my p probability is 0.34. And of course, if I raise the sample size, it changes the shape a little bit, or if I change the probability, it may change the shape a little bit. But in any case, let me now show you what the proportion distribution would look like, right? So if this red trend over here on the right, that's the what the binomial distribution would look like for the number of border collies you find in a sample of dogs at the dog park. Well, then this green distribution over here is kind of the same distribution, but now it's squished to fit between 0 and 1. Now instead of having 0 and, let's say, 40 as the lower bound and upper bound of the possible number of border collies that you might have in a sample of 40 dogs, now we're saying that 0 and 1 are the lower bound and upper bound of the proportion, right? Because you can't have a negative proportion of border collies, and you can't have more than 100% border collies, right? So the whole distribution has to fit between 0 and 1, but I want you to notice it inherits the same binomial shape. It's just squished together a little bit more, which means that if n times p times 1 minus p is greater than 10, then this is still approximately a normal distribution because it has the same shape. Okay, Again, just review of some Chapter 8 stuff. This is no longer a review of Chapter 8, but it is an important preliminary. Just to notice, whenever you see your textbook use this notation, so you see z with the little subscript alpha divided by 2, what that means is they want you to evaluate the quantile function, or QF for quantile function, and we're going to evaluate the quantile function at the point 1 minus alpha over 2. Notice alpha over 2 is what we're going to put into the subscript. So if, for example, I give you this z subscript 0.05, that means alpha over 2 is 0.05. So this would be my normal distribution quantile function evaluated at the point 1 minus 0.05. So that would be the normal distribution quantile function evaluated at the point 0.95. Now, where's the normal distribution quantile function and how would you evaluate that? Well, you go to your TI-84, we click second VARS. Number 3 says INV norm, and number 3, that's going to be our normal distribution quantile function. Sometimes the quantile function is called the inverse cumulative distribution function, and so that's why the INV is there, is because that stands for inverse. But in any case, when you see this z subscript alpha over 2, we're going to evaluate this INV norm in your calculator at the point 1 minus whatever your subscript was. So we select INV norm. Here where it says area, that's where we put in the 0.95. And then you, of course, have to supply the mean and the standard deviation of your normal distribution for which we're doing the quantile function for. So, if you have a mean of 0 and a standard deviation of 1, this would be the correct way to load it up. Okay. So if you see this again, and I'm sure you will see this symbol again, make sure you know what it means and how to calculate it in your calculator. So here's an example. Suppose I want to know what proportion of Midland College students own a car. And so what I'm going to do is I'm going to conduct a survey of 100 students. And in my survey, of course my survey size is 100 students, so n, my sample size is 100. X is 77, so that means I find 77 students have a car. So that would mean that my sample proportion is 77 out of 100. Remember, simple proportion is just x over n. And so this would be 0.77. Okay, so you know that there's probably about 5,000 Midland College students and not just 100. The real population proportion, if I were to somehow survey all 5,000 students, which might be kind of difficult, the real population proportion, we don't actually know that. We've calculated a sample proportion, which in theory should be close to the population proportion. But let's say that just for kicks, we think that the population proportion is 0.74. Well, then what I've calculated, my sample proportion of 0.77, that's just a little bit off of the population proportion. And what you're going to find is that in almost every single case, your sample proportion does not match your population proportion exactly. It should be close, but the probability is, very, very tiny that your sample proportion is really going to match your population proportion. And so what we're doing today, whenever I talk about confidence intervals, is we're going to develop some sort of margin of error and say that, yeah, the only thing I can really calculate in this life is the sample proportion, but we're going to put that sample proportion, which is my best guess or my best estimate of the population proportion, we're going to put that in the middle of what we call a confidence interval. And so that confidence interval now is going to tell us I have a certain degree of confidence. Maybe I'm 90% confident or 95% confident or 99% confident that the real population proportion falls inside of this confidence interval. That's centered around my best guess. It's centered around my sample proportion. And that's what we're going to talk about today, is how do you determine the width of this confidence interval? Or how do you determine the lower bound and the upper bound of a confidence interval after you've already calculated the sample proportion? Because given, this data, the x and the n, well, it's really easy to calculate the sample proportion, right? You just divide x divided by n. But now we're going to do a little bit of real statistics. We're going to say, given a certain degree of confidence, what is the interval over which I'm pretty certain, pretty confident that my real population proportion is going to fall. So anyways, being able to understand that and able to interpret our results, that's the most important part of the chapter. So hopefully that discussion makes sense to you. Some of this may be exactly what I said. Even the sample proportion itself is a random variable, right? So it's going to change depending on which students you randomly select for your survey, right? There's 5,000 students at Midland College. You're taking a random sample of 100. If you then the next day take a different random sample of 100 students, you're going to calculate a different sample proportion. It is a random variable. Like we talked about in Chapter 8, we have a formula for the sample standard deviation of this random variable, of this sample proportion. So you can use S subscript p hat to talk about that. And finally, getting to the root of what we're doing today, calculating this confidence interval, we say that a 95% confidence interval contains 95% of the most likely values of the population proportion. So we're first going to have to calculate a certain level of significance. And if I say I want to have 95% confidence, that's what we're going to put on the left side of this equation. It's 95%. On the right side, we're going to write 1 minus alpha times 100%. And this is actually an important little equation for us to memorize, how we determine what is my level of significance, what is alpha. Well, we write down my desired confidence. And so what if we have a 90% desired confidence? Well, 90% desired confidence would be 90% equals 1 minus alpha times 100%. And so if I divide both sides by 100%, well, 90% divided by 100%, that's 9 out of 10, that would be 0.9 equals 1 minus alpha. So that means alpha must be equal to 1 minus 0.9. So that means in this case, the one I just came up with, that alpha would be 0.1. And you can use the same line of reasoning here that I just drew on the bottom of the slide to come up with the fact that in the case I've printed on the slide, my original example here, for 95% confidence, that alpha should then be 0.05. So we always write alpha as a decimal, and basically alpha is just what's missing between your desired degree of confidence and 100%. Okay. Step number 2 says we want to calculate z with subscript alpha over 2. And I sort of promised you that this would come up, and I told you that you should memorize this particular equation, definition of z subscript alpha over 2. Knowing that my alpha is 0.05, alpha over 2 is going to be 0.025. Just divide 0.05 by 2. So then 1 minus 0.025, or 1 minus alpha over 2, would be 0.975. And if we evaluate the quantile function here at 0.975, I should get a value of 1.96. So let's try this. I'm going to go to second VARS. We're going to go to 3, which represents my normal quantile function. I'm going to set the area to be 0.975 this time. Mu is 0 and sigma is 1 for the standard normal distribution. And I may have misspoken earlier in the video, because anytime you see this z, we're going to let mu be 0 and sigma be 1. Z sort of stands for the idea of the standard normal distribution. Remember, we used the z to talk about the z-score, and in an earlier chapter we talked about how the process of standardizing a random variable, was just basically calculating the z-score. So anyways, trying to tie this all together, when you see that lowercase z, think the standard normal. So mu is 0 and sigma is 1. And, maybe gratefully, your calculator has 0 and 1 as presets. So if you forget this on an exam, just leave those alone. Leave the mu is 0 and sigma is 1 whenever you are evaluating the quantile function. So in any case, we get this quantile function is 1.96, just like it shows in step 2. Then we're going to calculate a margin of error, which means we set capital E to be our margin of error. This z subscript alpha over 2, that would be my 1.96 we just calculated. And then this s with subscript p hat, well, the s subscript p hat is, in fact, on the previous slide, right? It's this little formula here. So for our example, let's calculate s subscript p hat. Well, x is 77, n is 100, and p hat was 0.77. So for us, this is going to be the square root of 0.77 times 1 minus 0.77 divided by 100. So this is going to be the square root of 0.77 times 0.23 divided by 10. So putting in square root of 0.77 times 0.23, that's my numerator here. And then I want to divide that by 10 to get my final answer, 0.042. Okay. That is my lowercase s subscript p hat. And that's what I'm going to put in here, is 0.042. So then my confidence interval for my example is going to be p hat minus the margin of error. Well, let me first calculate that margin of error, I suppose. So I'll put in 1.96 times 0.042. Really, it should be 0.0421 because that 8 will round up, but it shouldn't change the answer too much. And I get about 0.082. No, 0.082. So that's not right. So my confidence interval, again, the lower bound is p hat minus the margin of error. So it's going to be 0.77 minus 0.082. And that will give me 0.688. And the p hat plus the margin of error is going to be 0.77 plus 0.082. So the confidence interval, again, is centered around p hat. The upper bound is p hat plus the margin of error, and the lower bound is p hat minus the same margin of error. And so that puts the p hat in the center. So again, this is my lower bound. My lower bound is 0.688, and my upper bound is 0.852. That's how you do a 95% confidence interval for this particular example that we had. Just to visually look at this, my sample proportion was 0.77. And again, this purple box represents my confidence interval, where my margin of error was 0.082. So that's going to be the width from my sample proportion to the upper bound of the confidence interval. And again, that's also the width from my sample proportion out to the lower bound of my confidence interval. And so again, the way you interpret this, you're looking at this purple region, you say, I actually have 95% confidence that my true population proportion, if I were to somehow survey all of the students at Midland College, that true population proportion will fall between 0.688 and 0.852. Just calculating the sample proportion doesn't tell you the true population proportion. That's still a little bit unknown to us. A few things to notice, though, before we move on, is that that margin of error is basically the width of the confidence interval, or half the width of the confidence interval. You multiply times this s with subscript p hat. And in calculating this, we divide by the square root of n, but that means if n grows larger, then s of p hat, or s subscript p hat, is going to get smaller. So for a larger sample size, that's going to reduce this lowercase s. And if that's reduced, that means the margin of error gets smaller. So basically, for a larger sample size, your margin of error is smaller, and your confidence interval shrinks. For a larger sample size, your 95% confidence interval is going to be a little bit slimmer. It's not going to be as large of an interval. And that means that you have the same amount of confidence that your real population proportion is within a smaller range of possibilities, and that's good. You know, you want your confidence interval to be as short as possible, so you want to have a large enough sample size, right? One more skill in this section is determining the required sample size for one of these types of surveys. So step number one, you need to decide on the desired degree of confidence. Do you want to be 90% confident? Do you want to be 95% confident? Do you want to be 99% confident? Of course, everyone wants to be more confident, so the 99 or 99.9% degrees of confidence might sound really attractive. But also keep in mind that the higher the degree of confidence you want, then the larger your sample size has to be. And so that can sometimes run into like budget or time constraints, depending on what type of survey you're doing. So you want to pick the highest degree of confidence that you can afford to do, basically. And you can never have 100% confidence. That's just not going to, it's not going to work. If you had 100% confidence, that means your level of significance would have to be 0, because you would want 100% equals 1 minus 0 times 100% over here in step 1. And then for alpha equals 0, you're actually asking about the quantile function for the normal distribution evaluated at just the number 1. And let's try that just to show you that that's not going to work. If we go to second VARS, I go to INV norm, which is the quantile function. If I evaluate at the area 1, what will my calculator tell me? Well, that's saying 1 times 10 to the power 99, just because your calculator, I guess, doesn't really grasp the idea of infinity. But that's a huge number, and really the true answer here to this question is infinity. So it's saying that your margin of error would have to have infinite width, which is, again, it's not nice to have. I mean, your confidence interval wouldn't tell you anything if it were infinitely wide. Okay, sorry for the tangent. Back to our little skill here. Number 1, decide on your desired degree of confidence. You want it to be high, but not outside of your budgetary constraints. Step number 2, you solve for alpha, just like we have done before. You put your desired degree of confidence on the left, and on the right side of the equation, you write 1 minus alpha times 100%. Solve for alpha. Number 3, you're going to calculate z with subscript alpha over 2. And so you just divide this by 2, so alpha over 2 would be 0.025 in this case. And then you evaluate your quantile function there. You decide on your margin of error in step 4. So this is no longer something we calculate, but we're going to just choose what do you want your desired margin of error to be. You always want your desired margin of error to be smaller rather than larger, so you want to choose something that's small enough right? Large margin of errors wouldn't really tell you anything, so you want something relatively small. But the same thing applies as number 1. If you make your margin of error too small, it might exceed your budgetary or time constraints that you have for your survey or experiment. So you have to give a little bit of width to your margin of error. Basically, you're deciding how much of a margin of error can I tolerate. Step number 5 is to calculate your n value. So n is our sample size, and this is the whole idea that we're talking about here, is how do you determine the required sample size? Well, lowercase n, that is our desired sample size. And one way you could do it, if you already have a really strong idea of what that proportion should be, then where it says p hat, that's where you're going to put your best guess. So you're going to do p hat, which is just your best guess at that proportion, times 1 minus p hat times z subscript alpha over 2, which you calculated in step 3, divided by capital E, which you decided in step 4. And then, of course, after you divide those, you want to then square it. And that calculates your sample size. If you don't have a good idea of what p hat should be, or you don't have a strong idea of what that population proportion is, you don't have a best guess, then the next best thing you can do is just to plug in 0.25. You might ask, why 0.25? Well, 0.25 is actually the largest possible value you can get from multiplying p hat times 1 minus p hat, because if p hat were 0.5, this would be 0.5 times 1 minus 0.5, which is equal to half times half, which is equal to 1/4. If you choose any other value for p hat here, like if you choose p hat as like 0.1, that'd be 0.1 times 1 minus 0.1, which is 0.09, right? That's clearly smaller than 0.025. Sorry, 0.25 I mean. So in any case, that 0.25 is just a conservative number to plug in, because that's actually the largest value you could possibly get. And so without having any idea of what the population proportion might actually be, the safest bet is to assume it's 0.25. Okay. After using this formula, I prefer that you use this formula unless your online homework tells you differently, then I want you to round up. So if you get n is equal to 3.2, let's say rounding up would mean setting n is equal to 4. So if you have any decimal after the integer, round up to the next highest integer. Okay, so hopefully we get that procedure. We have a couple of examples that I'll try to work through quickly. Example number 2. I want to know what proportion of Midland residents own a dog. And there's a whole bunch of Midland residents. Let's say there's 100,000 residents in Midland. So that would be way too many people. It would be hard to do like a census. It would be hard to sample every single Midland resident. So I'm never going to know the population proportion. What I can do is conduct a survey of residents where I only survey a few residents, like 100 or 200 residents. If I want a 90% confidence interval with a margin of error of 0.05 or less, how many residents do I need to survey? So I'm asking, what would be my sample size if I want this margin of error and this degree of confidence? Well, we just follow the instructions on the previous page. So I've already decided on my degree of confidence, 90%. I've already decided on my margin of error, so steps 1 and 4 are taken care of for me. Step 2 says I solve for alpha. So I set 90% is equal to 1 minus alpha times 100%. Divide both sides by 100%. Gives me 0.9 equals 1 minus alpha. Solve both sides for alpha, and alpha is equal to 1 minus 0.9. So alpha is 0.1. That is step 2 here. Step 3 says I need to calculate z subscript alpha over 2. So if alpha is 0.1, alpha over 2 is 0.05. Calculating alpha over 2 means I have to take the quantile function at 1 minus alpha over 2. So I'm at 1 minus 0.05, or 1 minus alpha over 2 is 0.95. And again, in my calculator here, I do second VARS, then normal inverse, or INV norm. Area is going to be 0.95. I leave mu and sigma alone, and I get 1.645. 1.645. That's my z subscript alpha over 2. I should say 1.64. I'll only keep 3 significant figures most of the time. 1.64. Then step number 5 says we need to calculate this. My sample size n will be equal to 1/4 times this z subscript alpha over 2 divided by capital E all squared. So let's do that. I have 0.25 times open parentheses. My z subscript alpha over 2 is 1.64 divided by my capital E margin of error that we wanted was 0.05. Close parentheses, I need to square the whole thing, and I should get 269 for my sample size. All right, so it's 268.96. Of course, we always round up. That's what step number 6 says. We need to round our sample size up to the nearest one. So my sample size required is going to be 269. That's how many Midland residents that we need to survey if you want to have 90% confidence in your confidence interval with a margin of error of 0.05 or less. I recommend that you take a look at this yourself. Pause the video now. Go ahead and try this example on your own. See if you can figure it out. And then you'll watch my solutions starting now. So I want to know what proportion of Midland residents own a house. And I'm going to conduct a survey of, let's say, 300 residents. And I find that out of this sample of 300 residents, I find that 116 of the respondents own a house. And what we're going to do is we're going to construct a 99% confidence interval so we can see, if I want 99% confidence of where that population proportion lies, then how wide does my confidence interval have to be? Of course, it's going to be centered around my sample proportion, which is just x over n. For us, that means 116 divided by 300. And that's going to be 0.387. For my sample proportion, again, we're not really going to be able to know the population proportion because it would just be a little bit infeasible, if you're conducting a survey, just because of budget constraints or time constraints. It doesn't really seem feasible to, survey every single Midland resident and get a response from every Midland resident. But that's why we're calculating a sample proportion, which is our best guess at what the population proportion will be. And then we're constructing this confidence interval, which is just a way of admitting we don't know exactly where the population proportion is, but we figure with 99% confidence that it's within a particular interval. Anyways, really briefly, let's go back over our procedure. So number 1, I need to determine what my level of significance is. And so for this example, I set 99% equal to 1 minus alpha times 100%. So divide both sides by 100%, and this is 0.99 is equal to 1 minus alpha. So that means alpha is equal to 1 minus 0.99, which means that alpha is equal to 0.01. Okay. Then alpha over 2 is going to be 0.005, and 1 minus alpha over 2 is going to be 0.995. If I want to figure out what is my z subscript alpha over 2, that's going to be z subscript 0.005. I have to evaluate my quantile function of the standard normal distribution at the value 0.995. So let's try this. Second VARS 3 for my quantile function. I'd have in 0.995. Finally paste, and that value is 2.58. Let's see what else we have in our procedure. I need to finally calculate my margin of error, which is going to be that z value times the standard deviation of the distribution of the sample proportion. So that is the square root of my sample proportion times 1 minus my sample proportion divided by n. And so let's do that really quick. This standard deviation of the sample proportion is going to be square root of sample proportion times 1 minus sample proportion divided by square root n. And remember, my sample proportion is 0.387. And so my sample size n is 300. So this is pretty easy to do in the calculator. We're going to do p hat, 0.387 times 1 minus p hat. So 1 minus 0.387 divided by my n, which is 300, and all of that's under one big square root radical. And so that's 0.0281. Okay. So then finding the product of these, that's going to be my margin of error, that z subscript alpha over 2 times the standard deviation of the distribution of the sample proportion. That's my margin of error. So I write E is going to be 2.58 times 0.0281. That gives me 0.0725. And now remember that your confidence interval has a lower bound at the point sample proportion minus margin of error. So my lower bound is going to be 0.387 minus my margin of error, 0.0725. So my lower bound here is going to be 0.315, we'll say. And then my upper bound of my confidence interval is going to be 0.387 plus 0.0725. That's 0.46. And this is the lower and upper bound of my confidence interval. Another way you could write the confidence interval is just writing 0.387 plus or minus 0.0725. Sorry, I wrote that really poorly. But you could also write your confidence interval by writing your sample proportion plus or minus your margin of error. Let me rewrite that over here. You can write sample proportion plus or minus margin of error. That's just another way to represent this confidence interval. So you might see that sometimes. You might see 0.387 plus or minus 0.0725. That's another acceptable way to represent your answer. Okay. Last thing I'll say is there's a shortcut on the TI-84 to doing one of these, since we can actually go back and redo example 3. Trying this, we're going to click the Stat button, we're going to highlight Tests, and then we're going to select A on there. So let's try that. We're going to go to Stat button, over to Tests, and then we're going to find A. And the title for A is 1 proportion Z interval. So we're talking about the confidence interval for just one proportion, one population proportion. The Z refers to the idea that we're using the standard normal distribution quantile function in there. And INT stands for interval. So select that. My calculator is going to ask me what was my X. And for us, that was 116. That was how many respondents to my survey said that they owned a house. N is going to be the number of people I surveyed. So this is my sample size of 300. The confidence level I wanted here in example 3 was a 99% confidence level. So where it says C level, I put in 0.99, and I just click calculate. And it tells me I have a sample proportion of 0.387, which is exactly what we got. And it tells me my confidence interval lower bound should be 0.314. Again, very comparable to what we have. And an upper bound of 0.459, which is again very comparable to what we have at the 0.46. If you want to figure out what is your margin of error after you've done it in your calculator like this, what you need to do is take your upper bound minus your lower bound and then divide by 2. So I want you to do 0.459 minus your lower bound of 0.314. That gives you sort of the length of your confidence interval. But remember that your margin of error is just half of the difference between your upper bound and your lower bound, right? So we're looking at this picture. Your sample proportion lies in between your upper bound and your lower bound. So that means you have 2 margins of error for the entire width of your confidence interval. So we do upper bound minus lower bound, and then we divide that difference by 2, and we find that my margin of error should be 0.0725, which for our example at the end, my margin of error was 0.0725, and so it looks like we got the right answer both ways. All right, see you in the next video.